Hello everyone, I'm Lance Fernandes. I'm a PhD student under Dr. Asif Khan at Georgia Institute of Technology, Atlanta, USA, and I'll be presenting our work on comparative study of channel materials for ferroelectric NAND application. This is the work that we presented at International Memory Workshop 2025. So starting with the outline, I will start with motivation and introduction for this work. It will be followed by understanding the key performance matrix in FE NAND for different channel materials. I will go more in detail about the materials and other aspects as we go in the next slides. And finally, I will conclude my talk. So, in order to increase the bit density, we have to increase the number of layers in the vertical NAND flash device structure. So, in order to increase the number of layers, we have to reduce the spacing between the adjacent word lines. So, as we are performing the Z pitch scaling to reduce the adjacent word line spacing, to increase the number of layers and to increase the bit density, ferroelectric materials have been heavily explored as an alternative oxide material for the conventional charge trap flash NAND. Many institutions and companies such as Samsung, SK Hynix are exploring ferroelectric materials for the future NAND flash technologies. And these ferroelectric materials as an oxide, they are compatible with the vertical 3D NAND process flow as well. So when we are using ferroelectric materials, there are certain design constraints that we need to adhere to. The very first one is the ferroelectric oxide thickness should be as thin as possible. Typically, it should be less than 19 nanometer to meet the tight industrial process constraints. The write voltage should be less than or equal to 15 volts, and a large memory window is desired. So memory window in the context of a vertical NAND flash is the difference between the two extreme device threshold voltages. For example, if L0 and Ln is my two extreme device VT, then my memory window in NAND flash is defined as the difference between these two VT states. So a large memory window is desired because it will enable us to have multiple VT states in between, and it will enable multi-bit capability, which is required for NAND flash applications. So how to get this? So how to get a large memory window? Typically in a standard FEFET, where only a 19 nanometer ferroelectric material is used, let's say hafnium zirconium oxide, then in a pure 19 nanometer SZO oxide stack, the maximum memory window that we get is approximately 2.4 volts. This memory window is typically not compatible with the NAND flash applications. However, keeping the overall thickness same to 19 nanometer, if we insert a dielectric material in the oxide stack, then we can see a significant memory window enhancement where we get a memory window of approximately 7.5 volts, and this memory window is compatible with the NAND flash applications. So there has been a lot of works done recently where different dielectric materials are inserted in the ferroelectric oxide stack to achieve a memory window which is larger compared to a ferroelectric only oxide stack. So in the case where a dielectric material is inserted between two ferroelectric layers, that is conventionally called as a laminated FEFET. Keeping the ferroelectric oxide same, which is the laminated FEFET that I mentioned before, in order to achieve large memory window, what is the impact of different channel materials on the NAND performance for the same oxide stack? So considering the same laminated Fe oxide stack, there are different channel materials that are compatible with the 3D NAND process flow. So we try to understand what are the different channel materials and how is their performance for the same laminated oxide stack. So the different channel materials and their details are mentioned here. The very first is the polysilicon channel. It is a state of the art which is used in the current NAND flash technology. It has large grain boundaries which can affect the mobility of the channel. It has a high thermal budget which is greater than 600 degrees Celsius, and polysilicon channel can have a good quality interlayer. Silicon is typically known to have a good quality channel interlayer. Then the next material we have is AOS channel, which is amorphous oxide semiconductor. And AOS channel examples are IWO, IGZO, IGO, etc. And these materials, they are not used in the current NAND flash technology, but they are explored as a potential channel material for future NAND, FE NAND flash generations. They have a low thermal budget because they are deposited via ALD. And another advantage of AOS channel is it can completely eliminate the need of an oxide interlayer. Finally, we can have a single crystal silicon channel. So a single crystal silicon channel typically have significantly low grain boundaries and almost negligible grain boundaries, and hence their mobility is higher compared to a polysilicon channel. And there has been a lot of recent works done, such as metal-induced lateral crystallization, where the amorphous silicon in the 3D NAND is crystallized in a way where the grain boundaries are significantly reduced to an extent that their performance becomes comparable to that of a single crystal silicon channel. So this is also not used in the industry currently, but it's been explored significantly as a possibility to use it for future NAND flash applications. So in this work, we compare the key performance metrics such as memory window, write voltage, retention loss, etc. For amorphous oxide semiconductors and polysilicon channel FEFETs. And we also compare these results with the single crystal silicon channel results that we have demonstrated in our previous works. And we try to understand how the overall performance is impacted for the same laminated Fe oxide stack. So these are the structural details and the process flow for the devices that we made at the Georgia Tech clean room. And this is the polysilicon FEFET. We confirmed with the TEM that the polysilicon channel have different crystal orientation, confirming the polysilicon nature. And this is the TEM for an IWO FEFET. So the AOS channel, we can have IWO, IGZO, IGO, etc. But we use tungsten as a doping because tungsten is typically known to have a higher bond dissociation energy, which can improve the bias stability. And hence we chose IWO as the channel material for the AOS channel FEFETs. So now let us try to understand the memory window performance for different channel materials for the same laminated Fe oxide stack. Again, a large memory window is always desired because it will help us to have multiple VT states to enable multi-bit capability. So here, the very first is the polysilicon channel. In case of a polysilicon channel, we see that the write voltage is approximately 16 volts with a memory window of 5.5 volts. And if we use the same laminated Fe oxide stack, in case of an AOS channel, we see that the write voltage is 13 volts and minus 14 volts respectively, and we get a large memory window of 9 volts. So the first thing that we see here is that the write voltage is reduced by approximately 2 to 3 volts compared to the polysilicon channel. So the write voltage reduction in AOS channel primarily comes from the absence of the oxide interlayer, which reduces the voltage drop across the oxide interlayer and reduces my overall write voltage. At the same time, we also see that the maximum achievable memory window in AOS channel is approximately 1.5 times higher than the maximum memory window achieved in a polysilicon channel. So let us try to understand the reason for this. So in case of a polysilicon channel, we have an oxide interlayer. So when we apply a positive voltage on the oxide gate metal, the ferroelectric polarization is aligned in a way where it is pointing down, and the positive charges are as shown here. So when we apply a positive voltage, that can lead to trapping of electrons in the channel interlayer. So is if we see here the ferroelectric polarization charges and the charges from the interlayer traps, they are opposite in nature, and therefore these IL traps counteract the ferroelectric polarization charges. Because of this, the ferroelectric polarization charge is not entirely reflected on the channel, which reduces my write efficiency, and thus it reduces my memory window. However, in case of amorphous oxide, when we apply the same positive voltage, the ferroelectric polarization is aligned in the same way as we showed for polysilicon channel. Here, since there is no oxide interlayer, there are some Fe channel interface traps, but the polarization charges are primarily screened by the electrons that are present in the channel. So since these are mobile electrons, and since the ferroelectric polarization is primarily screened by the charges present in the AOS channel, the channel becomes more conductive, and it significantly improves the program efficiency and increases my memory window as well. This we can also see in the IV curves. In case of a polysilicon channel, my program VTH is approximately -1 to -1.5. However, in case of my IWO channel, my program VTH is approximately -6. This is because in case of IWO channel, the ferroelectric polarization during the program pulse is primarily screened by mobile electrons, and it makes the channel more conductive and reduces my device's threshold voltage in a much more efficient way compared to the polysilicon channel where the polarization is screened by the IL traps and they both counteract each other. So now, here we have a benchmark plot of memory window versus write voltage. So here we try to compare the memory window from our work to memory window that was obtained in the previous work for different channel materials. And overall, what I would like to show here is that the AOS channel typically tends to have a higher memory window compared to the monosilicon channel, which is single crystal silicon, and polysilicon channel FEFETs for a comparable write voltage. Uh, I would also like to mention the high speed operation of IWO channel FEFETs. So typically in the conventional charge trap flash NAND, the program speed is approximately 10 microseconds. So what we try to see here is that can we achieve write speed of lower than 10 microseconds in IWO channel FEFETs. So we keep the program amplitude constant to 13 volt and -14 volt, and we change the pulse width from 20 nanoseconds to 10 microseconds. And we can see here that as we are increasing the pulse width, the memory window is also increasing, which is because we are giving more time for the ferroelectric to switch. And from this we can see that AOS channel FEFET can exhibit a high switching speed which is in the range of nanoseconds. Thus, AOS channel devices have a larger switching speed or a high speed operation compared to the current polysilicon channel devices. So the summary of memory window comparison for different channel is shown here. The very first one is the polysilicon channel, which has the lowest memory window, which we showed before. And the IWO channel, or the amorphous oxide semiconductor channel, has the largest memory window. And the monosilicon or single crystal silicon has a memory window which is somewhere in between for the both. So after understanding the memory window performance, let us try to understand what is the retention performance for these different channel materials. So in case of a retention performance, retention is important because the devices threshold voltage should not shift over time because these are non-volatile devices, and if the devices VT shift, then that can lead to overlap and read errors, which is undesirable. So ideally, having a robust retention where the device's threshold voltage is not shifting over time is desired for better retention performance. So here, considering the same laminated Fe oxide stack, we try to compare the retention performance for different channel materials. So in case of a polysilicon channel, we see that the memory window is lower as I showed before, but the device is programmed and erase VTH, they remain stable over time and there is very negligible memory window loss or negligible VT shift over time. Same thing is observed in single crystal silicon channel as well. We see that the memory window is higher as we compared to polysilicon channel as we saw before. And the device's erased and programmed threshold voltage remains mostly stable over time, and there is significantly low memory window loss over 10,000 seconds. And then we have IWO channel or amorphous oxide channel FEFET. So here we see that the initial memory window is very large as I showed before. However, over 10,000 seconds, we see that the program VTH is significantly reduced, and it reduces my overall memory window significantly at 10,000 seconds, which is undesirable. So in this slide, we have a retention benchmark for different laminated Fe oxide stacks in our work and in the literature. So my x-axis is my memory window at t equal to 0 seconds, and y-axis is my memory window at t equal to 10,000 seconds. So ideally, if my memory window, if there is no shift in the device's threshold voltage, my memory window should remain same, and my points should lie on y equal to x line. That is what we see for most of the laminated Fe oxide stacks in our work and in previous work. However, that's only true for single crystal silicon channel and polysilicon channel. In case of an AOS channel, we see a significant memory window loss of more than 50% at 10,000 seconds. Similarly, we compared our work on amorphous oxide IWO channel with the other works that were done previously on different channel materials such as IGZO. And from this we can see that the memory window loss, which is my y-axis, is comparable for different AOS channel materials as well. And say similarly, we compared our work on polysilicon with the other works that are done on polysilicon channel for Fe NAND. And we can see that the memory window loss on polysilicon channel is relatively much lower compared to the AOS channel devices in our work and in previous works as well. This in general shows that AOS channel devices without an interlayer tend to have a higher memory window loss compared to polysilicon channel FEFETs, where the memory window loss is significantly low. So in this work where we showed the retention loss for AOS channel, we do not consider an interlayer, which tends to increase my memory window loss over time. However, there has been some recent works where it is shown that incorporating a channel interlayer in AOS channel devices can significantly improve the retention performance and reduce my memory window loss significantly at larger times. There has been this work from a group in KAIST, which they presented at IEDM 2024, where they inserted a channel interlayer in amorphous oxide FEFETs. Here they have used an aluminum oxide interlayer, and by doing appropriate IL engineering to reduce the oxygen vacancies, they show that the memory window performance can be significantly enhanced. But again, adding a channel interlayer can affect the memory window performance because of the reasons which I mentioned in my previous slides. So the summary of retention performance in laminated oxide stack is as follows. Polysilicon and single crystal silicon channel have significantly low memory window loss at 10,000 seconds. However, AOS channel FEFETs without an interlayer have the highest memory window loss or a largest memory window loss compared to the other channel materials. However, using a channel interlayer, as I mentioned before, can significantly reduce the memory window loss, but that could possibly come at the cost of reduction in the memory window because of the presence of oxide interlayer. So let us try to understand the mechanism of retention loss in laminated stack on polysilicon channel. So in case of a polysilicon channel, we see that the device's threshold voltage do not change over time, and the memory window is stable, thereby leading to robust retention even at 10,000 seconds. So in order to understand this, we did some modeling, and we presented the work in our previous work at IRPS 2025. So without going into much details of that work, the brief mechanism is that there are some charges that are present at the ferroelectric dielectric interface, and these charges present at the FEDA interface are the charges which leads to an enhancement in memory window, as I mentioned earlier. And over like long periods of retention time, since these charges are present deep inside the oxide stack, they cannot detrap easily because there are thick ferroelectric SO layers on both the sides. And since this memory window enhancing charges, which are responsible for enhancing the memory window, do not detrap over time, the memory window remains stable for long periods of time. However, in case of amorphous oxide channel, we see that the array state remains stable, but the program state is significantly affected where the memory window is significantly degraded at 10,000 seconds. So in order to understand this, we have a hypothesis which we are also currently working to model on. So at t equal to 0 seconds after applying a program pulse, the ferroelectric polarization is aligned in the direction which is shown here, and we see that this ferroelectric polarization is primarily screened by the electrons that are present in the channel. And these electrons make the channel highly conductive, thereby significantly reducing my threshold voltage, as I mentioned before, on the program side. And at the same time, since we apply a large bias, there are some oxygen vacancies that are also produced in the channel. We get this oxygen vacancies from the neutral oxygen vacancies, which will basically produce positive oxygen vacancies and give away two electrons. So at t greater than 0 seconds after long retention times, the electrons that were initially screening the polarization, they tend to recombine with the positive oxygen vacancies, as we see here, in order to form a fixed oxygen vacancy, because that is energetically more favorable. So this electrons recombining with the positive oxygen vacancies will reduce the number of electrons in the channel, and it will deplete the channel, and hence it will increase my device's threshold voltage over time. And since my screening electrons are becoming less over time, and since they are getting depleted over time, that increases my threshold voltage, which is causing the reduction in the memory window performance. Finally, let us try to understand the pass disturb performance for IW and polysilicon channel FEFET. So pass disturb is important because if we are trying to access the specific cell in the NAND string, then we need to apply a pass voltage on the unselected cells in the string. So this pass voltage is typically the threshold, the highest threshold voltage of the device. So what we do is that we try to see what is the effect of applying pass voltage on the erased state and the program state. So we set the device in either the program state or the erased state, and we apply pass voltage cycling, where we apply a pass voltage equal to the highest VT value of the device, and we cycle it at 50 microseconds at a time. So we see that in both polysilicon and IWO channel, there is a slight increase in the device's VT value as we increase the number of pass cycles, pass disturb cycles. And this increase in VT primarily comes from the electron trapping that is happening near the interface, which is increasing my device's threshold voltage over time. And similar trend has been observed in both the cases where the device's VT is increasing over time. We also compare the ISPP performance for IW and polysilicon FEFET. So in order to compare the ISPP performance, we set the device in the array state and increase the program voltage incrementally. So a larger ISPP slope is always desired for high speed operations. And what we see is that in case of IWO channel, the max ISPP slope is larger compared to the polysilicon channel, polysilicon channel, which which is beneficial for high-speed operations in NAND devices. To overall conclude my talk, memory window in EOS channel devices with no interlayer is largest as we see here, and it also has a lower write voltage for same laminated Fe oxide stack compared to polysilicon and single crystal silicon channel. The memory window loss in polysilicon and single crystal silicon is the lowest, and the AOS channel FEFET without an interlayer has the highest memory window loss. However, performing channel interlayer engineering on AOS channel FEFET can significantly improve the retention performance. With that, I would like to thank you, and I would like to thank you for your attention. And I would like to thank our sponsors, SRC Supreme and Samsung Electronics from Korea.